Okay, this is problem number 4 on your pretest. I talked about some of this in class. I think it is the hardest problem that's on the pretest. So we have a great white shark. They're known for breaching the water when they're hunting for seals. So we have this shark in midair. Assume that it flies straight up and straight back down. It wouldn't happen in real life, but it makes this problem a lot easier. The shark is completely out of the water for only 1 second. So going up and coming back down only takes it 1 second. It says consider the point where the shark left the water as time equals 0 and that position as y equals 0. Part A, calculate the speed the shark has as it leaves the water. Once again, start with your knowns. So what I told you in class is the easiest way to approach this problem is you know the shark goes up and comes back down. If we only think about half of that motion, it makes this problem a whole lot easier. So for the rest of this problem, we're only going to think about the upward motion of the shark. Now, if it took it 1 second to go up and come back down, then it only took half that time just to go up. So the delta t we're going to use for this problem is not that full second, but half of it. 0.5 seconds is going to be the amount of time it took it to get to that maximum height. Okay, other things that we know, in midair, gravity is going to affect it. So we have that acceleration due to gravity of negative 9.8. Okay, in addition, gravity is trying to slow that shark down. So when it comes out of the water, that pull of gravity is slowing its velocity. So as it goes higher and higher and higher, it's getting slower and slower and slower until it reaches that top height and it's slowed all the way down. So at that maximum height, the velocity final will be 0. Now we're starting to see some stuff to work with. Remember, this whole time we're trying to find the speed as it leaves the water. We're looking for VI. Using that information, we have enough to do that. If you'll notice, we have VF, we have gravity, we have delta T, VI is included in the problem, but nowhere have we even mentioned the height yet. So since this problem has nothing to do with delta Y, we use equation number 1. So VF is equal to VI plus acceleration times time. The only problem is we're looking for VI. This is an equation for VF. So we have to solve this equation to get VI by itself. It's really simple to do. Right now, VI is being added to acceleration times time. The opposite of adding that would be subtracting it. So we're subtracting that acceleration times time from both sides. Minus AT, minus AT. Those will then cancel out over here, and you're just left with VI. So the new equation that we'll have is VI is equal to this side, which is VF minus acceleration multiplied by time. Now we just plug stuff in. So velocity initial is equal to velocity final, remember was 0, minus our acceleration of negative 9.8 multiplied by the time in the air, which is just that half second, 0.5. So if you notice we have a negative of a negative. That means this answer will end up being positive. So the answer for this is simply 9.8 times 0.5, which gives you 4.9 meters per second. That's our speed as the shark leaves the water. Part B asks us, how high did the shark jump out of the water? We want to find that maximum height, that delta Y. That's not hard to do. We know all this information already, and now we know velocity initial. So if we're looking for an equation for delta Y, we don't have to look far. Equation number 2. So for this problem, delta Y will equal velocity initial multiplied by time plus 1/2 our acceleration multiplied by time squared. Once again, don't forget the square. Starting to plug things in, delta y will equal velocity initial of this 4.9 we just found. 0.9 times the time, which is still that ½ second. We don't want to do the full second because then it would be back to the bottom. We want to know that maximum height. So we use 0.5 for our time. Plus 1/2 our acceleration, which is negative 9.8, multiplied by the time, still that 0.5, but we have to square that. So doing a little bit of math here, 4.9 times 0.5 would give us 2.45 plus 1/2 times negative 9.8 gives us a negative 4.9 multiplied by 0.5 squared, so 0.5 times 0.5 will give you 0.25. So delta y equals 2.45, oops, sorry, pen's messing up, 2.45. This will be a minus 4.9 times 0.25 gives you 1.225. Okay, last step mathematically is just to subtract those two. So 2.45 minus 1.225 gives you your final answer, which should be at 1.225. I'll round to 1.23. So even though it looks really impressive, the shark is only getting about 1.23 meters above the water. Okay, last couple parts of this problem is we have to graph this. So when you're graphing his motion, remember on the problem it said that you're starting from at a time of 0 and a position of 0. So on a position graph, what that means is you're starting right at the origin. So on your graph, we're starting here. He launches up in the air in the positive direction. So this means that our slope has to start going up. It's starting positive. Over time, gravity is slowing that velocity down. So as he reaches the top of his motion, he's slowing down. So this slope that it starts with gets more and more flat over time until he reaches the top, and it's completely flattened out. He's at a speed of 0 when he's at the top. Then he'll start to fall back down, and as he falls down, he's speeding up. So this flat slope that we have starts to get more and more steep in the negative direction until he reaches back down to the water where he started. Okay, for velocity. Remember, you get your velocity graph from the slope of your position graph. So looking at these slopes, it started off positive. In the middle, he had a slope of 0, and at the end, his slope was negative. So that means your velocity, starting out positive, in the middle of the motion, the velocity was 0, and at the end, it ended up negative. If we connect this, we're just going to get a straight line going through that axis, showing that it was a constant acceleration because it was a nice even slope that whole time. For the last graph, acceleration, we saw that it was a nice even slope saying that our acceleration was constant. Remember, gravity is causing the acceleration, and it's always that negative 9.8 value. So all we have to show for the acceleration graph is just a constant negative acceleration. Sorry, that should be, I'll have to redo it here. Just a completely flat line on that negative side of our graph.